Well, good morning and welcome to Humke's Study from wherever you are. I thought I'd take a few words to talk about homework 22. I've had a lot of questions. The question I'd like to focus on right now is the beast. When you found the length of the crease of the beast, several people indicated that they must be doing it wrong. They got the wrong answer. And everything looked good, but the answer didn't coincide with the picture that they plotted. And there is an issue in the beast. This is why it's called the beast. I'll put up a little video about it and something you need to be careful of when you're parameterizing. This is not just algorithmic stuff. You can't just sort of plug and chug blindly. You have to pay attention to what's going on. There are subtleties here, and the beast points one of these out. But today I want to talk about spherical coordinates and how spherical coordinates work. So spherical coordinates, in my opinion, are the real polar coordinates of higher dimensions. So let me, I could introduce these a couple ways, but let's do it this way. The spherical coordinates have three variables, typically labeled rho, theta, and phi. These two are geometrically angles. This is a distance. And this is equal to rho cosine theta sine phi, rho sine theta sine phi, and rho cosine phi. So let's look at a little arithmetic right away. And let's just look at those two terms are polar coordinates in two variables, where this would be r. So r cosine theta, r sine theta is polar coordinates. If phi is fixed, so that phi is fixed, then this value is fixed in both of them. And so let's fix phi for a moment at pi over 2. If you fix phi at pi over 2, then this last term is 0. These two terms are 1. So you do indeed get polar coordinates. So in the xy plane, this is the same as polar coordinates. So the first thing to notice is that that is the case. So phi equals pi over 2 tells you that. Let's take an arbitrary phi, fixed phi, and let's add up x squared and y squared. So this is constant. So when I add them up, I can factor that out, and rho I can factor out. So I'll get a rho squared in both terms, and I get a sine squared phi in both terms. And what I'm left in the first term is cosine squared theta. And then the second term sine squared theta, which is 1. So x squared plus y squared is simply rho squared sine squared phi. And if you add that to the z squared, you can factor out a rho squared, and it tells you that x squared plus y squared plus z squared equals rho squared. So we've eliminated one of the variables. More importantly, you can tell what rho is now. If you take the square root of both sides, rho is the distance between a point x, y, z and the origin. So that's the first thing to notice. I'm going to erase this work and draw myself a little picture here. Typical XYZ coordinate system. You take any point here, fix this point XYZ, then rho is equal to that distance, the distance between X, Y, Z in the origin. Okay. So this tells you, for example, that if rho is fixed and theta and phi, they both go between 0 and 2 pi, full range for both. We won't use both going between 0 and 2 pi, but just if you did, what would you get? You would get, since rho is fixed, this takes on all possible values between, well, cosine can be anything between -1 and 1, but the distance remains the same. So what you're going to get if rho is fixed is a sphere of radius rho centered at the origin. So if you fix rho and then let the others vary, this is the picture that you get. Let's take another look. Let's fix theta and see what we get. So erase this picture. We'll let the other two vary. And for the moment, let's just take pi over 4 so that we're looking at something. Identifying the polar line again with the x-axis. Okay, so let's look at theta equal pi over 4. Well, one point that satisfies that is when phi is pi over 2. If phi is pi over 2, then this term is 0. And these two terms are just polar coordinates in two variables. So if we look at theta is pi over 2, that would be this line here. Pi over 4 rather. Theta is pi over 4, gives you this ray of lines. And these are when phi is pi over 2. And rho can be anything, so you get this whole ray for sure. What else do you get? Well, you can get any, by adjusting phi, you can get any number for cosine between plus and -1. So times rho will be any values between minus infinity and plus infinity. If phi just goes in a smaller one, then you could keep rho positive. But for sure, what you get is everything above this ray. So everything above and below this ray, this kind of half plane here, is what you get for a fixed theta. So theta will give you the angle, you might say, between a given point and the y equals 0 plane here. And now let's take a look at phi. Maybe we'll do that by taking a particular point in three-dimensional space. So here is a point x, y, z in three-dimensional space. So that distance there is rho. And this point, if we project down to the plane, this lies on one of these half planes. And this distance is theta to that half plane, or from the y equals 0 plane, the xz plane, to this point is a certain angle. And so let's see what, in this instance, what phi is. And you notice that if phi starts out to be 0, then this term is just rho, And if phi is 0, these terms get zeroed out. So phi equals 0 is the z-axis. If phi is pi over 2, then this term zeroes out, and these two terms are 1. So then you get, then the point would be on this line here. So this is when phi is pi over 2. And in general, phi will give you the angle between this vector and the z-axis. So this vector is depressed from the z-axis by a certain angle, and that is the angle phi. Now, it's not necessary to know what these things are geometrically to use them, but it can be very helpful, especially in applications. So rho is the distance between a point x, y, z and the origin. Theta is the angle that this vector makes with the xz plane. And phi is the angle that this vector makes with the z-axis. So geometrically, that's what these things are. Let's take a look at the derivative of this. So sp prime of rho, theta, and phi. We've got an x, a y, and a z, so we'll have 3 rows to this derivative. And we've got 3 variables, rho, theta, phi, so we'll have 3 columns to this derivative. And so here we get, I'm going to just use C and S to save myself a little space here. But here, for the first one, I'll get the derivative with respect to rho is the cosine of theta, sine of theta. The derivative with respect to theta is minus rho sine theta sine phi. And the derivative with respect to phi is rho cosine theta cosine phi. For the next row, for the y here, derivative with respect to rho is sine theta sine phi. The derivative with respect to theta is rho cosine theta sine phi. And the derivative with respect to phi is rho sine theta cosine phi. And finally, the derivative of this last one with respect to rho is the cosine of phi. The derivative with respect to theta is 0. And the derivative with respect to phi is minus rho sine phi. So if we were finding this determinant by hand, I would expand by, say, the last row perhaps, or the middle column, because they've got a 0 in it. But the expansion contraction factor then is the determinant of this derivative. And when using spherical coordinates, you will need this expansion contraction factor. So, and this is easily, you can find this by hand, or you can use Mathematica to find it, but it's a good idea to try to find what this is. I'll leave that as an exercise. I want to go a little farther with this, and I want to talk about the elliptical coordinate system. It's similar. So actually it is ellipsoidal because it's 3 dimensions. And to begin with, I'd like to look at our elliptical coordinate system. So an elliptical coordinate system for r and theta in the plane has 2 radii. So it's got an A and a B, and it would be AR cosine theta, BR sine theta. And A and B are usually chosen to be positive. They don't have to be, but usually they are. To notice what this is good for, you could find a relationship between these variables. And so if we take the x and square it and the y and square it, we don't get anything in particular, but if we divide by these a and b squareds, or think of dividing x by a before you start, then this is r squared cosine squared theta plus r squared sine squared theta, which is r squared. And so you get the equation x squared over a squared plus y squared over b squared equals r squared. Now, if this is constant, so if you have x squared over a squared plus y squared over b squared equals a constant, like 1, for example, that tells you if you use these elliptical coordinate systems, the radius 1 will describe as theta changes between 0 and 2 pi, radius 1 will describe this entire ellipse. Or if you want xy less than or equal to 1, then taking r between 0 and 1 describes the entire interior of this ellipse, because for elliptical coordinates, r squared is equal to this thing. So this is very nice, and theta is again a central angle like it is with polar coordinates. You can remember that the determinant of this, the expansion contraction factor in this case, is easy to remember. It is just pi AR, AB. If A and B are equal, then it's a circle, and A and B are equal would be the radius of that circle. You get pi r squared. But if A and B are different, this is the expansion contraction factor. So this is just the area of an ellipse with x radius A and y radius B. Now, with the ellipsoidal coordinate system, it is similar. So we'll look at an ellipsoidal system, and I'll use rho, theta, and phi this time. I'm going to begin with the spherical coordinate system that we just did. So this would be cosine theta sine phi, rho sine theta sine phi, and rho cosine phi. So this is the one we just had. The ellipsoidal one is different only because it puts an A in front of this, and a B in front of this, and a C in front of this. So now we've got an ABC. And now, again, in the old one, we had x squared plus y squared plus z squared equals 1 or equals rho squared in spherical coordinates. But now, in order to take advantage of that arithmetic, you have to divide x by A, y by B, and z by C before you square. If you compute this, x divided by A is the old spherical coordinate quantity squared. Y divided by B is the old spherical coordinate quantity squared. Z divided by C is the old spherical coordinate for Z divided by C. So this is again going to give you rho squared. As a consequence, if this is constant, it gives you an ellipse and an ellipsoid in 3 dimensions, where the x radius is a, the y radius is b, the z radius is c. And if you wanted the inside of an ellipsoid, so you're integrating over a football-shaped region, so this is less than or equal to 1, this tells you that you're going to have rho between 0 and 1 will describe the entire interior to that ellipsoid region. And then depending on what the ellipsoid region is, if you want all of it, then theta between 0 and 2 pi, and phi between minus pi over 2 and pi over 2. I guess I didn't show that, but phi, the natural range for phi is between minus pi over 2 and pi over 2. So these are the ellipsoidal coordinates. If you found the expansion contraction factor for spherical coordinates, you get 4/3 pi r cubed. The expansion contraction factor for ellipsoidal doesn't have an r cubed, it has an ABC here. So the determinant of the corresponding derivative ends up to be 4/3 pi times the product of the 3 radii, radius in the x, radius in the y, radius in the z. So how do you use this stuff? So let's put up a function, and I won't do it completely, but I'll show how to do it. Let the temperature at any given point, x, y, z, be given by some formula. In a way, it doesn't matter what that formula is. Find the average temperature over the sphere, over the, let's say, the ball, meaning the inside as well, of radius 2 centered at the origin. Find the average temperature. So let's call this ball B. So what we want to do is integrate the temperature over the ball divided by the integral of the one function over the ball. And this is the answer. So to actually find this numerically, though, we need to do these 2 integrals. So let's see how you do these integrals. They're both kind of work the same. So the integral of the temperature over the ball, I'm going to change to spherical coordinates. So I'm going to take the temperature of the spherical coordinates, which are rho, theta, and phi. And I'm going to integrate those over the ball. So I'm just going to rewrite the thing in spherical coordinates. And we'll need that expansion contraction factor because this represents a change of variables. So expansion contraction factor necessary because I'm not using x, y, and z. Since it's over the ball, rho will go from 0 to 2, ball of radius 2. And so rho will go from 0 to 2, meaning you take the temperature and you plug in rho, theta, and phi using spherical coordinates. 4/3 pi r cubed. This should be d rho cubed. D rho. Theta will go between 0 and 2 pi. And phi will go between minus pi over 2 and pi over 2. If you integrate over a larger region than minus pi over 2 to pi over 2, what happens is that you duplicate some of the ball. So it's the same problem with the beast. If you duplicate some of the region, then the integral will show that. So your function, your parameterization, your substitution should be 1 to 1. And minus pi over 2 to pi over 2 will make it 1 to 1. So this is the answer. So this gives the integral of the temperature over the one ball. And once you do this integral, if you do this integral, then dividing by 4/3 pi times 2 cubed, the volume of the ball will give you the average temperature. So this is how this one works. Spherical coordinates, 3 dimensions. Okay, I think that's it. Have a good afternoon, and I will see you soon.